All right, let's get started. So the Sapiens 2, the topic was chosen by Wei, but he is not here. He once was our classmate. And this morning I received his message. Sorry, I cannot present it. It is too difficult for me. Okay, so I roughly created this copy of slide and presented to you. Okay, this is a very why he chose this topic because he is interested in post estimation, and between the discussion. In the discussion between him and I recommend. Okay, he originally chose old paper, then the DW post. It was published 3 years ago, and I told him, why don't you choose Sapiens this one, because this is the state of the art method, and he agreed with me, and he agreed to present this paper 7 days ago, but soon he changed his mind. Okay. Never mind. Let's see. This is a huge work. So first, what is sapiens? So it is a Latin word. Homo sapiens, just human beings. Okay. Then homo is human. Sapien is wise. So no matter how. So this is our current evoluted result. Homo sapien, right? Oh, never mind. Meta research just pick up the word sapiens as their model's name. That's all. Just keep in mind. Okay. And there are two versions, Sapien 1. And in the beginning, there's no Sapien 1, just Sapiens. And this year, they will publish the Sapiens 2 in ICLR. And when is ICLR? See here, ICLR will take place next month. So this is a very, very new paper. It was just accepted 2 months ago. But it was released, when is it was released? Okay, yeah, it was released just this month. So very, very new paper, right? Again, let's talk about the Sapiens 1. It was accepted by ECCV 2024 and it got the award, Best Paper Award Candidates. It means when it competed with another paper for the Best Paper Award, well, another paper won, but this paper got the candidates. However, it's a great honor because you see more than, say, I forgot the number of submissions for ECCV 2024. I estimate around 7,000. I don't know the detail. Okay, but however, it is the second best paper. You can see how difficult it is to get this award. Okay. Right. Okay. So let's consider what is input and output. So input is an image content in a human, at least one person. Okay, but there can be multiple persons, like this one. And what is output? There are 4 different types of outputs. First, post estimation. So you can see they will predict the landmark localization coordinates. And then they just visualize those coordinates by drawing some lines between those connected key points. And the second type is segmentation. They segment the human region into 28 classes. And for example, hair, this is clothing, left R, left hand, right hand, left arm, right arm, left. And this is the depth, okay, the distance between every point of the person to the camera. And the final, the fourth is the normal, the direction of the surface of the human. Okay, so how do they do it? Oh, now you know the input-output, how to do it. Okay, easy, just train a VIT vision transformer. Okay, so how to train it? Well, since there are 4 tasks, so they pre-train a backbone for the 4 subtasks, all downstream tasks. And once they get the backbone vision transformer network, then they fine-tune the pre-trained transformer for each of the 4 different tasks. Okay, so this is the approach. And okay, in the first step, they don't need any annotation. They only need, but here you see we have a lot of annotation, right? The localization points, the part. They only need those annotated training set in the second step for each task. All right. Okay. So for first, how do they train the backbone vision transformer? They use the masked autoencoder method. Well, this method has been published for many years. Okay, it first was released in arXiv and accepted by CPR. Okay, and let me remind you who is the first author, Kai-Ming He is the inventor of ResNet, the extremely famous ResNet. And the masked autoencoder has been cited more than 14,000 times once it's published today. So you can see it is a highly impactful paper. Okay, so what is the masked autoencoder? So it means, what is the input of the masked autoencoder? You have an image, but you removed some patches. This means just mark them as a gray region. And you expect your autoencoder, which includes an encoder and a decoder, that they can reconstruct the missing patches. So that's the map. So this is a masked, and this is the autoencoder. Okay.
So you don't need to have a label.
You don't need to have any label. That's correct. You just need to prepare sufficient images, and remove some patches. And there are several ways to remove those patches. You can remove them randomly, or you can use certain patterns to remove them, right? So in their paper, they discuss the difference between masking approaches. So I should say, no, I do not show anything. Let me just show it. Okay, this is the masked autoencoder. So let me show it. Okay, so for example, you can see here, there are different approaches to do the masking. Randomly, or just it's a big block, or just use some grid. And will it affect the results or the performance? Yes, they do. Okay. And the randomly will generate the best results. Because why? Because when those patches are randomly removed, the remaining nearby regions, patches, can still bring in some information so that it can reconstruct those missing patches. But if you use a block, then you remove the overall very large region. It will be relatively difficult to reconstruct the region. For example, for this fox, okay, you can see it become relatively blurred compared with the randomly removed approach. And if you use a grid, then the problem is the reconstruct the image will have many apparent grid patterns. All right? So here, so they, as the meta researchers, they just use the NAE method to pre-train their backbone vision transformer. Okay. Okay, so let me, just as mentioned by Cam, they don't need any annotation. So that is the importance of that paper, because annotations are difficult to or expensive to create. You can, but it's expensive. If you just need to collect a lot of images, it is relatively easier. So why the NAE paper is popular? Because see the title. Masked autoencoder are scalable vision learners. You can increase the scale to a very, very, very large level. So that is important. Okay. So what does it mean? If you have sufficient data and sufficient computational resources, you can learn a very effective masked autoencoder. So this is the claim in Kai-Ming He's paper. Right? Okay, so in the Sapiens 1, how many images do they use? 300 million images. How many computational resources do they use? They use 1024 A100 GPU. And you know, one A100 GPU has 80 giga VRAM. So this is a huge amount. And they train those 1024 machines for 18 days. It's a tremendously abundant of computational resources. Meta is rich, so they are it's affordable for them. Okay. All right, and let's talk. So how do they compile or curate the human 300 million data set? First, they collect 1 billion images in the wild, and they ensure every image must contain at least one prominent person. But there can be multiple people. So this is the statistic of their final result. They have 17% ratio of images containing only a single person, and for 2, 3, 4. So most of their images contains at least 4 people in their image. Okay, but this is just the first step. Second, they apply a filter, because for some images there are watermarks, there are maybe some text or some artistic modifications. They don't want those images. They just want a very natural images containing human. So they apply a content filter to remove a lot of those pictures containing watermark and text. And finally, they want to ensure the people on the image are large enough and clear enough. So they apply an on-the-shelf person detector to retain images with confidence scores greater than 0.9. So it's very clear. The detector will predict, okay, this is really a human, not just something like a human. And the human is large enough. So they set a bounding box. The width or the height, either of the one, need to be greater than 300 pixels. Okay, so they collect a lot of clear human images. But next question, how do they collect the 1 billion images? 1 billion, this is a very large number. Because they are Facebook. When people upload their photos to Facebook, Meta has the right or the license to use them. This is the Facebook user agreement. Okay. So, okay. But recently, actually, as early as 2014, okay, they updated their user license. But recently, in this year and the previous year, the the law slightly changes because 10 years ago, the users are not so aware of their data was used to train any AI models. Okay, but currently something changed. So in Europe and in UK, users need to explicitly allow Facebook to use their photos to train AI models. Otherwise, Facebook will violate the law. But in US, okay, the default setting is allowed. All right, okay, can you access the human 300 million dataset? Yes, you can. If you want, you can submit an application to Meta Research. And if they approve, you will get an API key so that you can use the API key to access their photos on Emerald S3 service. And they will monitor your behavior. If you use it accordingly based on their agreement, that's fine, you can continue using it. If you violate or abuse, then they will disable your API key. All right, so okay, now we have the background knowledge about the data set, and let's take a look of the vision transform. I believe most of you heard of it, right? Have you used of it? Not yet. Okay, if not yet, so let me just quickly go through what it works. Okay, transformer. Transformer is a sequence-to-sequence model, right? So your input need to be a sequence, and your output will also be a sequence. That's a transformer. Transformer in the beginning was designed for language problems, for example, translation. You have prepare for example German sentence as an input, and through this network, you expect that it will generate an English version of a sentence. So that is a sequence-to-sequence translation. Okay. But how to modify the model for a vision problem? Okay, the approach. Okay, so this paper was published in CPR 2021 by Google Research. And their approach is, given an image, split the image into very tiny patches. So here is the example. Let's split this into a tiny patch. And for every patch, first, for example, how large will be the patch? Usually 16 by 16. So here you can see the keyword. An image is worth 16 by 16 words. So why they use the 16 by 16? Because this is their page size. Okay. Then, once you have a lot of patches, just arrange them as a sequence. First, you can apply a linear projection to project each page. So the page size is how much? 16 by 16. And there are 3 channels. So the number of elements or values within a patch is 16 times 16 times 3. Okay? And then you apply a linear projection to project those vectors to another vector. Then combined with the position encoding. Position encoding means this is the first patch. This is the second patch. It will inject another feature vectors and concatenate the 2 feature vectors into a new single vector. So it will be something like this. So this is the first patch and the content of the patch. The second patch and then the content of the second patch. And in the beginning, you prepared a special token. Usually it is the classification token. It is a learnable parameter. It is also a virtual vector. And add a special position embedding 0. So here you will have a sequence of token. Then through the existing transformer architecture. So this transformer architecture, it looks like you have an input, and there are several modules in a layer, and then you have multiple layers. So they are L times, layer by layer by layer by layer. It depends on your architecture. If you have more layers, you will have more learnable parameters within the multi-layer perceptron and the multi-head attention. Okay. Then go through, and those encoder layers, you will have a latent vector for each token, because the output of those input sequence is also a sync. Then you will have a decoder. Decoder is something like this. Okay, it is. Then through the decoder, you will reconstruct a sequence of images. So if you want to do a classification, then you just need to get the special token, the classification token in the latent space, and then apply a multi-layer perceptron projection to predict what the class would be for the input image. So this is a basic architecture of the vision transformer. Okay, then let's take a look. The timing Hertz mask autoencoder use vision transformer already. So let's see some examples. So this is the original input image, and this is the masked image, and they control the factor of the masking ratio. So if they max 75% of the input patches and train the masked autoencoder, then they can reconstruct the images result like this. But if they increase the masking ratio to 85%, they will generate with. So you see, more details are losing. If they increase to 95%, okay, you can just roughly get the structure of the input image, and a lot of details are missing. Okay. And these are results trained on the ImageNet 1K test training set, and then they want to ask another question. So what will be the classification result depending on different masking ratio? So this is their result. So there are two different approaches, because you see the mask autoencoder is a pre-trained approach. Once you pre-train the backbone already, and you need to fine-tune it as a classification task. So there are two different approaches. First, you can frozen those pre-trained parameters. So it will be the linear probing approach. It means you just when you pre-train the model for the classification task, you only update the weights in the latest layer. So this is the first approach. And the second is you can update all of those parameters in the vision transformer. Now that is the fine-tune approach. And they found that no matter they use the fine-tune approach or the linear probing approach, okay, the performance can keep in a very high level if they use the 75% masking ratio. What does it mean? It means the pre-trained vision transformer, the pre-trained mask autoencoder learned very good knowledge of the training set. Okay. Oh, yeah.
Why did they choose 75%? Because looking at that, actually it would seem like 65% would be a better place to collect the data.
Oh, okay, because for this one, they need to consider both cases. For this one, yes, 65% or 60%.
No, also for the second one, right? Because
yeah.
it was 71.8 at 80 and 71.8 at 60. So they should have sampled the data point at 65% as well.
65 here?
Yeah.
Okay. Let me enlarge it. But 65% is around 72.
Well, but you don't know, right? Because they didn't sample. You could do the same linear extrapolation from 70 to 80, right? If you look at 70, it's 73.2. And then 80, it's 71.8. Actually, if you did a linear...
Oh, do you mean they will go here? Do you mean there is an interpolation between 70 and 80?
Yeah.
No. The cross here means they set the parameter.
Yeah, so why did they not test 65 as well, is my point, because 65 would...
Oh, do you mean why don't they?
Yeah, why did they choose 75 specifically?
I don't know.
Yeah. It seems really weird.
Okay. I don't know. Okay.
I also had another question.
Yeah.
I think we've seen this, we talked about this before. So the images in the masking cases, they all turn out really blurry, right? Which you mentioned. And I think that's because of the loss and the specific training objective. Because the model is trained, I'm guessing, based on the difference between its predicted outcome for that pixel and the actual pixel from the training data. And so the models are trained, in VAEs in general, it's a problem. They're trained to be blurry, like predict the average when they don't know, because it minimizes the loss.
Well, first, I don't think they predict those masking region by average. The reason is, okay, see here. When they only have this input image, there are a lot of mask region, right? Why do they know there is an edge here? You see, they didn't see any edge of the top of the bus. But how do they know? Why their model know there should be an edge? Because they saw, okay, there are some similar images in their training set. So their model learned the parameters to predict that there should be an edge here.
Yeah, so they learned that, like, if you looked at the patch, right, they learned that because there is a left side of the bus, there should be a right side of the bus.
Yeah, that's right.
But because it's trained on, like, hundreds of buses, it doesn't know specifically which part of the bus, like, which type of bus should be on the right. So it shows an average of those 100 bus spaces.
I said, for if you use average, okay, I think the average have two meanings. The first is just the mathematical average. Okay. The second is their model learn something from the 120 images. Okay, and so that they predict there should be an edge, or what should be the content of the masked patches.
Yeah, so it's like the average in embedding space, or like the average of like on the manifold or something.
Yeah.
So, but it is because of the loss metric, I think, and the training objective. It's trying to predict the average bus, like in the.
Do you mean the loss function? Okay. Well, the loss function is simple because the loss function is the input is a mask region, but we know the ground truth. When the model generates a predict images, we will compare the mean of the square error between the output image and the ground truth. Okay. So what I want to say is, let's go back to here. Okay. Here, the model saw many patches here. Okay, they saw there are some blue patches here, and they saw there are some yellow patches, and they saw some gray patches at the bottom. And the model knows their locations. So from the limited input information, the model will assume this is maybe a school bus. Then using those information, for example, this is a white patch, and this is also a white patch. It means, okay, maybe the roof of the bus is white. So it predicts, okay, there are some a sequence of white patches, and there's a few yellow patches here, there. Yeah. So that's the power of the vision transformer. Because if you have a transformer, what does it mean? Every patch in the input image, because it will be a sequence, it will contribute through the attention mechanism to predict what will be the, let's just say, well, what is the information it should be carried through the transformer architecture. So as you see, convolutional neural network care about what? Local information. And the transformer, it can exploit the global information. Yeah. Okay, so this is the okay. Okay, so this is how the Sapiens2 use the masked autoencoder as its backbone pre-trained approach.
So they cut the decoder part and use the encoder part in that backbone, right?
Sorry, could you say again?
They cut the decoder part and use only encoder part as a backbone for Sapiens.
No. Okay.
Because the decoder part is used to fill the mask.
The decoder is used to fill those patches. Okay. And your question was, do they only use the encoder and disregard the decoder? Right? Let me see. Okay, let me see. Yeah, I think so. Because for their 4 subtasks or downstream tasks, they don't need to reconstruct the images. Yeah, so they only use the encoder. Yeah. Okay, so let's take a look of their demo. So this is a ground truth image, and okay. So what's the difference between this slide and the previous slide? Let me explain. In this previous slide, they use the ImageNet 1K, and there are 1,000 classes of the ImageNet 1K. And here, they use the human 300 million data set. So every image must contain at least 1 person. So here, all of them are humans. Right? Okay. So let's take a look. Okay. See here. Okay. Because the training set is share some common knowledge, all of them are human. So even though this is a 90% mask ratio, just according to this limited information, the masked autoencoder can still recognize that this is the part of the human face. And here again, this is a 95% okay, masking ratio. Okay, so this is a ground truth, this is masked, and the masked autoencoder can still reconstruct the images with this quality. It's very, very powerful. Okay. Right, so let's take a about the spec. So they train their input image resolution is 1024 times 768. The page size is 16 by 16. So there are 4 different architectures. 3B, 0.3B, 0.6B, 1B, and 2B. Okay, so what is the difference? The number of layers, okay, and the number of heads. Heads means in the vision transformer, there can be multiple heads. Multiple heads means you can use different heads to control different attention mechanism. So, in addition, what is the hidden size? The hidden size, okay, for the encoder, given an input image, and it will go through many layers. So this is a number of their layers, and they will generate a latent vector, right? So the dimension of the latent vector is the hidden size. So this is only the encoder part. They don't, just as Ken mentioned, they don't use any decoder. They pre-train their reinforcement model, but they only use the encoder. Okay. Yeah.
The batch size is very large.
Mm-hmm.
That's not normal, right?
Not normal because they use 100 GPU, A100, right? A100 has 80 giga VRAM, so it can use a very large batch size.
So they're just using the batch size to match the VRAM.
I think so.
Yeah.
Mm.
Yeah, that's crazy.
You're crazy. They are rich, so they can be very crazy.
Because you run into problems with larger batch sizes, right? Like you're making bigger updates on the bigger steps on the network or something.
Mm-hmm.
Maybe it's not as efficient for training.
I don't know because I never used the A100.
That's crazy though.
But as far as I know, if you use a large batch size, because they are batch normalization in the vision transformer architecture, so your generated result will be more stable. Okay, so now we have the impression of the pre-trained backbone. Okay, then if you train it for 18 days, all right? Okay, now it converges to certain stable condition. Okay, then you can use the pre-trained model to fine-tune then for the subtask, downstream tasks you want. So first is the post-estimation. So here, this is the example of their ground truth annotated data. So they use 308 point format. The name of the format is Galia. So let's take a look. The whole body 508 and the hand 40 and the face, there are 243 points on the face. Why do they need to create? Oh, let me compare this. So this is a Microsoft Cocoa dataset. Well, actually, there are several different formats to label key points on a human body. Microsoft Cocoa, there are only 17 points, and Cocoa was published in 2024. And then Google Media Pipe, there are 33 points, and Google Media Pipe was proposed in 2019. And there's typo. This is Cocoa whole body. This is published by a university. There are 133 points. So pay attention here. They are also compared with the Cocoa whole body and the Galiath. So what's the major difference? Face. Here we have 243 points. Okay, and here compare with this face and this face. Do you see the difference? Let me highlight. Okay, let me tell you. Pay attention to the ear. There are a lot of key points on the ear. And there are, for the eyebrows, there are an upper curve and a bottom curve of the eyebrow. Okay. And let's see this one. Okay, see, there are only 3 points on the ear, much less. And for the eyebrow, there's a single line, the upper boundary of the eyebrow. So for Metascadia's format, there are more details to describe the human faces. Why? because it's Meta. Remember, several years ago, Meta, in the beginning, it was named Facebook, but it changed its name to Meta. Why? Because they want to propose the Meta. That's right. Okay. And how do you model an avatar precisely? You need a lot of key landmark key points on a face. Face is very important message media or something like that. But how? So that's the reason. Here we see Sapiens2 use the 308 points. But there was the following question. Is this convenient to use? Nobody knows. They propose it. Will other people follow? The following researchers still use this format? I don't know. We need to see the progress for a few years. Okay. And I should say, for different applications, they have the users just only pick up the one most suitable for their application. All right. Okay. So this is the segmentation format. So let's see. This is the left hand, right hand. So the hair. Okay. So there are 28 classes. And okay. So the third and the fourth downstream tasks are depth. So this is after the depth. The brighter means the point of the human body is more closer to the camera. And the darker is the far distance. And this is normal. Normal means you need to, if suppose this is a surface, and you need to know the direction of the surface. Okay, so there's a question. How do they, now we know they need the annotations. Otherwise, they cannot train those 4 downstream tasks. How do they generate those annotations? All right, the answer is here. For the 2 downstream tasks, they use synthetic data. So this image, the 4 images you see here, are all synthesized. They have a background, and they use the 3D human models to create a figure set and pass the figure on the image. Okay, because this woman was generated through a 3D model, so they can very easy to get the depth information as well as the normal information. Otherwise, how do you label it? Okay. But however, for the segmentation and for the post-annihilation, they manually label it. They hire a lot of Turkers to do it. Okay. So let's see the size. For the post-substring task, there are 1 million annotated images on 4K high-resolution images. So you can imagine. Suppose they need to pay a Turker $1 for an image. They need to spend not just only 1 million. It must be multiple millions, because every Turkers will create some noisy data. So they need to hire multiple Turkers to label the same input image. And then maybe they will calculate the average. If the standard deviation is small enough, they will say, okay, those labels, annotations are good, accept. And then they may need to hire another Turker to watch those visualize the result to see whether those annotations are correct or not. So they need to spend a lot of money to create those labels, but they are rich, so they can do it. Let's enjoy it. Okay, and for segmentation, the size is only 1/10 of the pulse, because I think segmentation is relatively hard or more expensive to label because you need to create the boundary. Yeah. For pose, it's relatively easy. Just need to click here, click here, there. Right. Okay. So this, and then another. Okay. Where did they create those training images for the downstream pose attenuation task? In their studio. So this is the setting of their studio. They took those pictures indoor. Okay, so that they can accurately control those actors' poses and illumination, etc. Okay, so let's see about their result. First, they need for numerical evaluation, they need to create a data set first, and so that they can compare multiple methods on the same data set. So they created the data set called the Human 5K. It means there are 5,000 images, and they have the ground truth of those images. So this is the visualization result of their pose estimation. Okay, and this is a numerical comparison. So as I mentioned, DW pose, that is the paper originally picked up by Wen. And so that once I see this table, I told him, oh, okay, if you want to present a DW pose, I suggest present this Sapiens1. And but however, there is a Sapiens2, so it is better to present a Sapiens2 rather than Sapiens1. But however, this table was cropped from the Sapiens1 paper. So let's just take a look. So this is average precision and average regression. So let's explain the meaning first. Average precision is you have a lot of points, right, on the 2D plane. Are they correct? How far are they from the ground truth coordinates? So this is average precision. The larger the better. Okay. And the average regressions. For example, let's take a look. Here, you only see the upper body, right? So there is no lower body localization key points. If your algorithm detects there are some lower body key points, that's wrong. Okay. Or if, for example, okay, if your algorithm, so there are some hands, but the hand is inside the hairs, right? So for some algorithm, they may miss those key points. So your algorithm should detect those key points. If you miss them, then your recall rate will be lower. So this is an average recall. So it means if you have both high AP and high AR, it means your algorithm, post-attention algorithm, correctly detect those key points occurring on the image, and your localization are precise. So let's take a look. So here, for the body part, okay, the Sapiens version 1, the 2B model is the best. For foot, for face, for hands, all of them are best. Okay. Compare with the baseline DW pose, okay, there is a huge improvement from 53 to 61. So when this paper was published, okay, it is the state of the art. So that's the reason it was selected as the best paper candidate. Okay, for this is the segmentation qualitative results. Some, I should say, when we, okay, it looks nice, right? And again, there are some numerical comparison. So for their largest model 2B, it achieves the best performance compared with several state-of-the-art methods in 2024. Okay, so let's take a break. Okay, so let's continue. So this is the second task, segmentation. And this is the third task, depth explanation. So, okay, this is the state of the art 2 years ago, depth anything. And this is the Sapiens 1 for 1 billion model. Okay, so let's see. So how do you tell which one is better? Right. Let's take a look here, and let's enlarge this one. You see on the shelf there are a lot of wrinkles, right? Here, there are a lot of wrinkles, and okay. So in this, sorry, okay. On the result of depth anything, do you see any wrinkle here? No. But in the Sapiens 1, there are a lot of wrinkles. But what's the first is the depth, and what is the second column of the image? That is the gradient of the depth. So because when you only see the depth, you cannot see the changes or the details of the depth. But if you visualize the depth, the gradients, you can see how much it changes along on the surface of the depth. So here you will see, okay, those wrinkles are captured by the Sapiens 1 model. So that is the evidence to show their model is better than the state-of-the-art depth. Depth anything. Okay. And okay, so this is also the numerical evaluation. So their model achieved the best run except for this task. And that is the fourth one, the normal. Okay, so this is the Sapiens. So here, why they claim their results are better? Because if maybe you should see the smoothness. Okay, for example, for this suit, well, the two state-of-the-art method generated many, I should say, how should you say, what's uneven or variation, but their models generate a very smooth normal surface. Okay, so there's better. Yeah. Okay, and okay, again, this is the numerical evaluations. Their result on the two data sets, T-humans and HI40. Okay, they achieve very good result. All of them are the best. Yeah, one is for 1B and one is for 2B. Only at this. All right. Okay, and they claim their Sapiens model can be generalized for different domain. What is different domain? First, multi-human. As we say, their training set is 90%, 17% one single person, and 20+% for 2 person. And here, 1, 2, 3, there are 8 people on the image. Their model still works. And for age generation, so what I mean? This is a child, very young girl. It still works. And this is what? This is an egocentric video. Okay, there is no torso on the image. There are only arm, hand, and legs. It still works. So that's their claim. Okay, they released their code. I tried it. It is very easy to. Actually, not easy. I want to show you because it looks so nice. Wait a moment. Yeah, so see this demo. So attractive, amazing. Is it real? I want to test it. All right, fine. Okay. First, their document is understandable. It's a good. And just prepare a directory and download those models from Hugging Face, then you can do. But however, there are some problems. Let me explain why. Because the installation script was created 2 years ago, and then they didn't update it. So I just launched the installation script, and I encountered some problems. First, NumPy. They use NumPy 1.x, but the latest one is NumPy 2.0. They are incompatible. The second, they use the library nmpose, but also because the new version is incompatible with their code. And then PyTorch 2.4 version has the security protection. If your model file is not signed, they will not allow you to load it. But however, all of those problems can be solved. Yeah, just downgrade them to the 2023 version. Okay, so I just cropped some frames from the online video. Okay, and see, this is the post-application result. Looks good. Oh, so yeah, there are some mistakes here. And in addition, if you look here, you will also find some problems here. This is not so accurate. This is the eyebrow. The upper line of the eyebrow should be here, but it is wrongly labeled. Okay, and here the ear. The ear should be somewhere cover the whole ear, but it's wrong. And also the red points should be the upper bound of the upper lip, and this is also wrongly predicted. So there are some problems. Okay, and of course you see this is a false positive. Fine. Okay, but if the humans in the frames are smaller, can it work? Yeah, it still works. So yeah, basically it works. Yeah, basically it is a good model. Yeah. Because as you see here, okay, as you see, yeah, this image on the table, and they are not 100%, right? Because they test it on the 5K image size, the average position and the average record is just more than 60. Yeah, so no algorithm is perfect, and they perform good enough. State of the art. Okay, and for every image, they will predict the adjacent file. It contains all the coordinates and all the confidence scores. Users can read it, so it's good. And I use this laptop. Okay, there are only 8 GB VRAM, and it can run the 1B model. No problem. And I also test the 0.3B model. And 1B model is apparently better than the 0.3B model. But the problem is it runs slowly. The inference speed is just 1 frame per second. So if I want to run 60 images, I need almost 1 minute. So I cannot do it real time. But maybe, okay, I should say, this is a problem of my model, my machine. If I have a very powerful machine, A100, maybe I can run it real time. And there's another lighter version. It uses the B float 14 and 16. Do you know what it is? Okay, this is a new format. Okay. So I remember you know the IEEE standard for the floating points, right? Okay, so they are single and double. They are defined by IEEE. Okay, that is a typical or traditional format. And the B-flow 16 was proposed by Google because if you want to train an AI model, the scale is more important than the precision. So they split the 16-bit into a single side bit and 8 scale bit and 7 precision bits. Okay, so they can use just half of the 32-bit typical double floating point, and so that it can accelerate the inference speed and the training speed. Their GitHub web page claimed it can speed up the inference time for 4 times, but I didn't try it. Okay, fine. And now, yes.
So the light version is just used for 16.
For 16, what do you mean?
I mean the light version is used only the V for 16 format.
Oh, no. Yes, yeah, that's right. Okay, let's take a look of their web page. It will be very clear to know. So this is the light installation. Okay, and wait, where is it? Sorry, maybe in their README document. Yeah, basically yes. Okay. On their webpage, they provide 3 different formats. Okay, the truncated, the full 32 bits, and the original one, and the B float 16 format. Okay, and here, yeah. Now, okay. Well, I spent 1 hour to discuss the Sapiens1, and now, okay, let's show what is Sapiens2. Okay, so here, I just create a table so for you to get a idea what is Sapiens2. So first, it becomes larger. The input image resolution for V1 is 1K, 124 times 7800, and for V2, it becomes 4K, larger. And the model size, okay, they are 0.3, 0.4, 0, 1, and 2 for the V1. And for V2, let me see, can I see it? 0.4, 0.8, 1, and 5 become larger. Okay. And training set also increased from 300 million to 1 billion. Okay. And there are 2 additional tasks. First is a point map, and the second is Alberto. You will see the visualization later. They also updated the architecture. So just as Jai mentioned, do they use Dino? Yes. They use the concept of Dino in their updated, the V2 version. And I will show you a slide there. And for the segmentation classes, they added one more, the eye glasses in the V2 version. And the annotated training set become 0 in the original for the depth, and for the normal, they are only 0.1 million annotated training set. And in the V2, it was increased to 1 million. So it becomes a larger model. Okay. So let's see the improvement. Okay, so the left part is the V1, and the right hand side is the V2. So let's see, can you see the difference? Yes, see the hair. The Sapiens 1, 1B model, and the Sapiens 2, also 1B model. The model size is the same, okay? But let's see the hair. See the hairs here and the hairs here. You can see more details here. And for the, yeah, here, I think it is very, if you see the hair, it's very clear. You can see more details here. So this is the improvement from version 1 to version 2. And here you can see the teeth. The teeth is blurred, but here the teeth is very clear. Okay, and yeah. There is another improvement. They claim their backbone VIT encoder is become more stronger. How to prove that? It means, you know, the encoder will generate output latent space, right? If you use the latent space to find the nearest neighbor in a set of images, what will you retrieve? A very effective encoder should retrieve highly similar images, right? So for V1, take a look of the 3 images. Okay, so this is your query image, and this is the 3 images retrieved by Sapien1. Make sense? Yeah, makes sense. Background, blue sky. Foreground is the human, and under the ground, green yacht. Makes sense. Okay, but compare with the Sapiens2. So what's the difference? Number of people. For Sapien1, all the 3 most similar retrieved images have a single person. But in Sapiens2, because there are 4 people in the query image, all of the 3 images retrieves images containing multiple people. So this is an improvement. And for this one, okay, for Sapien version 1, the color, is similar to the query image. But for Sapien2, not only the color is similar to the query image, their activity is also identical to the query image. So this is a very significant improvement. Okay. And is there any? Okay. I think this one is very good because you see, for this query image, the 2 images are the same, right? This one, this is retrieved by Sapien, and this is by Sapien2. So yes, they retrieve effective image. But however, compare with the remaining 2 for this, and for this and this, which one is more similar based on our human concept, closer to the input image? I think this is better. Yeah. So this is improvement of Sapiens2. Okay, and so let me slightly explain. Okay, so there are multiple layers on the VIT transformer, right? And first, there is a special token, the learned classification token. If you retrieve the classification token at the latest layer and see its self-attention for those image patches to the classification layer, you will generate these results. So this is input image. And you generate this attention. What does this mean? It means the model clearly knows where the person is. So Jai, you must be very familiar with, right? Because this image, the similar images are also presented in the Dino paper. That's right. Okay, so let's talk about just to show the Sapiens2 architecture. Okay, so here, given an input image, it will create 2 views, a pair of views, from view 1 and from view 2. And what do they mean? Because this is from the same person, so the 2 different views should generate the same latent vector. So that is the idea of Dino. So in Sapiens2, because they are from the same company, so they use the idea of Dino. So okay, and then here you see the diagonal line here. It means the masked autoencoder. They removed some patches, and so masked autoencoder still exists in Sapiens2 architecture, but they incorporated the new multi-view self-stealing approach. Okay. All right, so let's compare the Dino V1. And so here you can see, not the Sapiens1. So this is Sapiens1. And you see the pulse. It is 63.4. And now it improved to 74.7. Okay, 2 years. Yeah, this is a huge improvement. And the pulse segmentation, pointer map, normal, and albedo. So all of them are now the new state of the art become the Sapiens2 5B. And okay, so let's compare visually. So here, let's enlarge it. Okay, so this is the segmentation result for Sapiens 1 billion. And see the difference. There is a clear difference. So what are they? Okay, they are, let's take of the original image. What are they? They are part of the clothing, not the hairs. And in Sapiens 1, they are they are not segmented from the crows, but in Sapiens 2, they do. And see here, because Sapiens 2 has the new class glasses, so here the glasses is separated from the human faces. And in this example, in Sapiens 1, okay, the lip and I should say, in Sapiens 2, the segmentation results are better compared at this corner and this corner. Okay, the upper lip is better segmented. So that's the improvement. Okay, and this is the list of the 29 classes. Okay, so this is a new task, pointer map. Pointer map means given the input image, okay, you will estimate their 3D localized coordinates of the human. If you have the 3D coordinate for every point, you can change the view angle. So here, okay, so this is input image. And this is the state of the art, the more NOGE published in CFR 2025. This is their NOG's output, and this is Sapiens2's output. So from this, you can get this. And if you rotate the view angle, you will get this image. Because you have the 3D point cloud data. You know the pixel of every point in the 3D space. So here is again, if you have the input image and you can extract the pointer map, then you can rotate. You can replace your camera location in the 3D space at any place, so that you can generate new images. Now, so this is the input image here. So this is the first angle, and this is the second angle. So you can see there are some white points here, right? Because from the input image, you don't know. You have no data there. So it will become white. It can be rendered unless you predict them.
Yeah, why didn't they do that? Because I guess they use synthetic data for the training. This one as well?
Let me see. Do they use synthetic data? I think so, yeah. I think they use synthetic data.
Because in the other tasks, they predict occlusions, right? Like they predict the hand if it's behind your head still. So then why did they decide not to do that here?
Oh, no, I mean, I should say, I guess that's because from this input image, there's no such data. I know there are some methods that can predict the unseen region, but I think Sapiens2 doesn't do it. They just faithfully predict the visible region.
Because I assume this is for like metaverse application as well. What's the idea?
I don't know.
Okay. Which would need the full 3D. So
Okay, this is the normal. Okay, so let's enlarge then. So again, this is okay. See, this paper, David, was published in ICCV 2025, the latest computer vision conference. Okay, so compare with David and the Sapiens2. Again, see the hair. The hairs is a very clear difference. The Sapiens2 outperform David. Okay, and here again you can see the hairs. Yeah, this is much more clear. And here you can even see the inside region of the head. So this is a very powerful model, the Sapiens2. All right, and a new task, Alberto. So let me explain what is Alberto. Alberto means the original color of the surface. So when you see, for example, when you see this image, okay, you will see the forearm is slightly brighter than other region, and here under the nose you will see a shadow here, right? The darker region. So Alberto means, can you give me the original image of that region disregarding the illumination? So it will reconstruct the Alberto region. So here you see the color of the front, the upper side of the forearm is the same as other region. And under the nose, you can see much more brighter color compared with the input image. So this is the goal of Alberto. And in Sapiens2, they created a new task. So this is the input image, and this is their predicted Alberto. Then this and this and this. Okay, yeah, right. Okay, but there is no comparison. So yeah, this is the end of introduction for Sapiens2. Okay, and let's see how much. Oh, I run out of the time. Sorry, I need to preserve time for when it starts low. Okay.